All right, let's just dive right into this explainer and uncover a massive hidden trap that haunts data scientists everywhere. We are going to explore exactly why standard, highly advanced machine learning algorithms spectacularly fail when they try to treat time like it's just ordinary data. So welcome to episode 1 of our documentary series, Inside Time Series.
To kick things off, I want you to picture a chaotic montage of the world around us. Think about stock market crashes wiping out billions in a matter of seconds, rolling weather patterns dictating global agriculture, shifting electricity demands lighting up entire continents, and the erratic beeping of hospital heart rate monitors keeping people alive. Now, at first glance, these things seem completely unrelated, right? One is driven by human psychology and finance, another by atmospheric physics, and another by human biology.
But what's genuinely fascinating here is the hidden structural reality connecting a beating heart in a hospital room to daily ice cream sales at your local shop. When you record this data, you aren't just capturing isolated numbers in a vacuum. You're capturing a sequence. Time is the invisible thread binding all these completely disparate events together into a singular mathematical concept known as a time series.
Here is the absolute kicker. Unlike ordinary independent datasets, where one row in a spreadsheet has absolutely nothing to do with the next, the very fabric of a time series means that today is inextricably tethered to yesterday. Classical statistics often relies on random sampling, assuming data points are totally independent. But the second time gets involved, that assumption completely shatters. I mean, you literally cannot shuffle the days of the week and expect the weather to make any sense. Time has a memory.
Chapter 2. Every time series tells a story.
So if we just stare at raw data, it usually looks like a chaotic mess. But a time series is actually made up of multiple hidden patterns all layered on top of each other. Take a look at this home energy consumption data over an 8-year period. You can instantly spot these really aggressive seasonal spikes hiding right in the middle of unpredictable, jaded fluctuations. In the summer, air conditioners are drawing massive power. In the winter, heaters are doing the exact same thing. It's not random. It's a highly structured response to the environment, all mixed in with the everyday noise of human behavior.
The very first layer we've got to peel back to understand this story is the trend. The trend is the long-term underlying direction of the data. It's the macro movement. Think of a steady, decade-long increase in global air travel, or conversely, the gradual death of video rental stores. It doesn't even have to be a perfectly straight line. It can change direction, but it tells us where the data is generally heading when we zoom all the way out.
And check out what happens when we visually smooth out the data. We actually extract that true signal from all the chaotic noise. This is an absolutely critical step in building your intuition before we ever touch complex math. You can clearly see how applying a filter, like a moving average, strips away those jagged day-to-day random jumps, revealing the actual beating pulse of the dataset underneath.
Now, as we dive deeper into these patterns, we have to be super careful to distinguish between seasonality and cycles. Seasonality runs like absolute clockwork. It's tied to the calendar, like holiday shopping spikes every December or a surge in ice cream sales every July. Cycles, on the other hand, rise and fall unpredictably, often over periods way longer than a year, like economic recessions and booms. Treating a completely unpredictable business cycle the same as a fixed seasonal month will literally destroy your forecasting models.
Chapter 3. Why forecasting is hard.
Okay, this brings us to a frankly devastating conflict. Standard AI has no inherent concept of time. If you evaluate your model by shuffling time series data using standard random cross-validation, you are mathematically allowing your model to time travel. You're basically asking it to learn from tomorrow to predict today. It creates this massive illusion of accuracy simply because the model has already peaked at the future. This exact statistical trap of temporal data leakage actually cost one specific coffee shop model £500,000 in just 12 weeks. All because the system was evaluated on data that hadn't happened yet in the real world. You have to use walk-forward validation if you want to simulate reality honestly.
And look, no matter how good your validation is, the existence of black swan events proves that forecasting is inherently about managing probability, never achieving total certainty. Just consider the 1987 Black Monday stock market crash, or the sudden, world-stopping onset of the COVID-19 pandemic. These are monumental structural changes and massive concept drifts that no historical pattern could have perfectly predicted. The rules of the game literally changed overnight.
Moving on to Chapter 4, Teaching AI to Understand Time. So how do we stop our models from cheating and help them survive these catastrophic distribution shifts? Well, we have to translate the passage of time into a language that algorithms can actually process. We start with the foundational concept of a lag.
A lag basically gives the algorithm a memory by explicitly feeding it the values from previous specific time steps. So instead of just showing the AI today's temperature, we feed it a feature representing exactly what the temperature was yesterday or exactly 7 days ago. We are literally hardwiring the past into the present features.
And by utilizing those lags, we introduce the concept of temporal dependence. This forces the machine learning model to acknowledge that the data isn't just randomly sampled from some bucket, but sequenced in an unshakable chronological order. It teaches the algorithm that the state of the world right now is fundamentally correlated with the state of the world just a moment ago. Finally, before we can apply a lot of classical forecasting models, we look for stationarity. Think of this as an idealized condition where the rules of the data aren't constantly shifting underneath us. It means the mean and the variance, essentially the average behavior and the volatility, stay relatively consistent over time. If a time series has a massive upward trend, it's non-stationary. A lot of traditional algorithms desperately need you to mathematically remove those trends to achieve stationarity before they can even begin to function properly.
Chapter 5. The journey begins.
Now that we've got our core vocabulary nailed down, let's map out the incredible engineering journey ahead of us in this series. Over the upcoming explainers, we're going to trace the entire technological evolution of forecasting. We'll start with the elegant simplicity of moving averages, graduate to the serious statistical power of ARIMA models, and then we'll cross the threshold into modern deep learning. We'll explore how neural networks like LSTMs remember the past, how transformers totally revolutionize sequence modeling, all the way up to the absolute cutting edge of foundational AI models like TimeGPT.
If you take away just one thing from this today, make it this. Time isn't just another column in a spreadsheet. It is a fundamental, physical constraint. It's a structural reality that our models must respect before they can accurately forecast anything. If you treat time like a standard feature, you aren't doing data science. You are doing time travel, and I promise you, reality will eventually catch up and break your model.
Next time on Inside Time Series, we're going to explore one of the simplest, yet most incredibly influential ideas in the entire history of forecasting, moving averages. We're going to roll up our sleeves and ask, how exactly do these simple mathematical filters manage to cut through all the chaotic, unpredictable noise of reality to find the true underlying signal? I will see you in the next explainer.